All right, welcome. Today we're going to tackle a question that sounds, well, almost too simple. But trust me, the answer unlocks this huge, profound secret about how our entire universe works.
So picture this, right? You're in a perfectly still room. No wind, no fans, nothing. The air feels totally motionless. So how fast are those air molecules actually moving? If your first thought was 0, well, you're in for a surprise. The real answer is way cooler and actually a fantastic story.
See, here's the thing. The most common speed for an air molecule is nowhere near 0. It's actually the result of this epic showdown, this cosmic competition between two fundamental principles of nature that are always at war with each other.
So let's meet our first contender in this competition. It's basically a universal tendency. You can almost call it nature's fundamental laziness. A ball always rolls downhill to its lowest energy point, right? It doesn't roll up. Well, it turns out molecules feel the exact same way.
Okay, before we get any deeper, we have to get one really important distinction straight, and that's the difference between velocity and speed. Velocity, that's how fast and in what direction. So 10 meters per second north, that's a velocity. Speed, on the other hand, is just the number, just 10 meters per second. This might seem like a small detail, but believe me, this difference is everything. A single velocity is one very specific point, but a single speed, that's a whole collection of different possibilities.
Now, this whole laziness thing is actually governed by a really cool rule in physics called the Boltzmann factor. And what it says, in a nutshell, is that for any single state of motion, the more energy it has, which means a higher velocity, the exponentially less likely it is to happen. It's like the universe just really doesn't like to waste energy on any one thing. So what does that mean? It means the most probable single velocity for any given molecule is 0, just standing perfectly still, because, that takes the least amount of energy. Now, if this were the only rule in the game, every molecule in the air would eventually just grind to a halt. But obviously that's not what happens.
And that's because our second contender is about to enter the ring. And this one isn't about which state is the most probable. It's all about how many states are even possible. This is purely a game of numbers. And this is where it gets a little bit mind-bending. Think about it. There is only one way for a molecule to have 0 velocity. One. It has to be perfectly, absolutely still. But how many ways can a molecule move at, let's say, 100 meters per second? Well, it could be going up, down, left, right, forwards, backwards, or literally any angle in between. There are just so many more possibilities. Here's a way to visualize it. Imagine a 3D space of all possible velocities. A really low speed, like 1 meter per second, that's like a tiny little sphere right around the center point. There just aren't that many different directions or vectors you can fit on the surface of that tiny sphere. But a much higher speed, that's like a huge sphere. And a huge sphere has a massive surface area, which means there are way more possible vectors, more ways to achieve that exact speed. Okay, so here's our showdown. We've got our two competitors facing off. In one corner, we've got the Boltzmann factor, screaming, slower is better, less energy. And in the other corner, we have sheer numbers, yelling, the faster you go, the more ways there are to do it. So, who wins this fight? Well, turns out neither of them wins outright. It's actually a compromise. Think about it. At really low speeds, yeah, the probability for any single state is super high, but there are just so few states available that your overall chance is pretty low. Then, at super high speeds, you've got a ton of possible states, but the Boltzmann factor just crushes the probability of any single one of them, making the overall chance low again. The real winner is that sweet spot right in the middle.
And what comes out of this beautiful balancing act isn't just chaos. Nope, it's a predictable, really elegant pattern that scientists can actually measure and use. This pattern has a name. It's called the Maxwell speed distribution. And it's basically a curve that tells you the exact likelihood of finding a molecule at any given speed. You can see how it starts at 0, it climbs up to a peak, that's our sweet spot, the most probable speed, and then it just trails off, because those really extreme high speeds become almost impossibly unlikely. So the math behind this is actually pretty elegant. The overall likelihood is literally just our two players multiplied together. You've got the possibility factor, that's the number of ways to move, which grows with the square of the speed, and you multiply that by the probability factor from Boltzmann, which drops off exponentially. You match those two together and bam, you get that perfect curve.
So let's get back to our original question. What is that most probable speed in our perfectly still room?
Well, for a nitrogen molecule, which makes up most of our air, at room temperature, it's about 422 meters per second. That is, get this, over 940 miles an hour. The air that feels completely still to you and me is actually a hurricane of molecules zipping around at literally supersonic speeds. Wild, right?
And this distribution curve is incredibly powerful. It's super predictive. For instance, we can ask it a question like, hey, what are the odds of finding one of those nitrogen molecules moving faster than, say, a blistering 1,000 meters per second? And the math gives us a precise answer. It's only about 1%. So yeah, it's possible, but it's really, really unlikely.
Okay, so this might all seem like just a neat party trick for figuring out how fast air is moving. But this whole way of thinking, this idea of carefully counting up all the possible states and then weighting them by their probability, this is genuinely one of the most powerful and fundamental ideas in all of physics.
This entire method gets bundled up and formalized into something called the partition function, which physicists just call Z. And you should think of it like a master key. Seriously. You just sum up all the possible states a system can be in, you weight each one by its Boltzmann factor, and this one single function, this one number, can tell you pretty much everything you need to know about that entire system.
The power here it's just incredible. Once you have Z for a system, like a gas in a box, a few simple mathematical turns of that key unlocks everything else. It's free energy, it's entropy, the pressure, the total energy, all of it. This simple idea, just counting possibilities, is the absolute bedrock of a whole field of physics called statistical mechanics. It's just such an amazing idea, isn't it? We started with a really simple, almost silly question about still air, and it led us to this deep, deep truth about the universe, that by understanding this battle between probability and possibility, we can unlock its fundamental secrets. It really makes you wonder, what else can we predict about our world, just by carefully, patiently counting all the ways something can happen?